PSSLab AVR Tuning. Keywords: Automatic Voltage Regulator AVR, Synchronous Machine Generator, Static Exciter Transfer Function, Frequency Response of Open Loop, Logarithmic Frequency Characteristics. Hi everyone, Davor here. In this video, I will demonstrate how to tune an automatic voltage regulator AVR operating in a closed-loop control system that includes a thyristor converter, a synchronous machine as generator, and a feedback transducer. The tuning method presented in this video is based on the system's frequency response characteristics represented on a logarithmic scale to calculate and determine the phase margin. This phase margin is then used to achieve an appropriate AVR tuning. We start with the general closed-loop control block diagram, including a controller, a power stage, a process, and a feedback transducer. The controlled value is at the output of the process. The feedback or actual value after the feedback transducer is subtracted from the target value in a summing point, creating an error signal as an input to the controller. For the generator voltage control by an exciter, the controller is meant as a PID controller, the power stage is meant as a thyristor converter, the process is meant as a synchronous machine or generator. The controlled value is the generator terminal voltage. In case of the static exciter, only the PI control algorithm is used. The PID control algorithm is typically applied to AVR systems with rotating exciter machines, such as brushless exciter. Procedure for overall transfer function in open loop. In this video, we will focus exclusively on the static exciter. Therefore, only the PI control algorithm will be considered. We will examine the transfer function of each block individually. First, we will express each transfer function in the Laplace domain. Next, we will convert it to the frequency domain and then represent it on a logarithmic scale. Finally, the gain or magnitude and phase responses versus frequency will be plotted in the Microsoft Excel using a separate worksheet for each block. In the final step, we will combine the individual block responses to obtain the overall transfer function on a logarithmic scale, which we also call Bode plot, in open loop. Based on the overall response, we will determine the appropriate PI controller gains required to achieve the desired phase margin. First, we focus on the procedure for the frequency response plot of PI block. Here in step 1, we have the transfer function of the PI algorithm in the Laplace domain. S is the Laplace variable, Kp is the AVR gain representing the proportional part, while the Ti represents the integral part. Then in step 2, we move to the frequency domain to obtain the frequency response by substituting S with J multiply omega, where the J is the imaginary unit. The result transfer function in step 3 is a complex number and therefore consists of the real and imaginary parts. Then in step 4, for the purpose of the frequency response plot, we convert the equation in 3 to logarithmic scale of base 10. The first plot shows the magnitude, which can also be interpreted as the gain or amplitude ratio, while the second plot shows the phase angle phi. It is convenient to work on a logarithmic scale because multiplication and division of transfer function magnitudes can be represented as addition and subtraction in logarithmic form. Finally, in step 5, we obtain the frequency response plot of the PI block for Kp 130 and Ti 4.08 seconds. This response is plotted in one of the Excel sheets. The left ordinate shows the gain in decibels, while the right ordinate shows the phase in degrees. The abscissa is expressed in Hertz rather than in angular frequency omega. Normally, if we perform these analyses in MATLAB, two separate plots would be displayed, the upper one for the gain and the lower one for the phase. The complete calculations in Excel, together with the corresponding Excel plots for the PI block and other blocks, can be provided upon request. Reference for the PI block for your detailed study can be found in IEEE Standard 421.5 Annex E. In similar fashion to PI block, here we have the procedure for the thyristor converter block and its frequency response plot. You can pause this video to look more in details for this block and next blocks, including procedure for the generator transfer function block and its frequency response plot. For the parameters used in this frequency response plot, please refer to calculation sheet, which forms part of this presentation. As I mentioned before, it can be sent to you upon request. Reference for the generator transfer function for your detailed study can be found in Power System Stability and Control by Prabha Kundur, Chapter 4, Synchronous Machine Parameters. And the measuring filter is the last block which needs to be considered in the control loop. Here is the procedure and its frequency response plot. After completing the individual transfer functions and their corresponding plots, we can now derive the overall open loop transfer function of the entire control system. First, we write the open loop gain, also called amplitude frequency characteristic, in step 1, and phase frequency characteristic in step 2. Both are the sum of each individual transfer function for amplitude and phase, represented in logarithmic scale. Next, in step 3, we plot both characteristics in an Excel spreadsheet and tune the gain Kp until the phase margin between 40 to 60 degrees is achieved. In step 4, the plot shows the open loop frequency response for the desired phase margin. Phase margin is determined at the frequency point where the gain characteristic, the red curve, crosses 0 decibel. The gain crossover frequency, which in this case is 2 Hz. In this point, the Kp is 130. At the same frequency, the phase characteristic, the green curve, crosses minus 135 degrees. The phase margin Pm at this frequency is calculated as difference between 180 degrees and 135 degrees, which give us 45 degrees. So the Pm or phase margin is 45 degrees, which is within targeted phase margin between 40 to 60 degrees. For your further study, it would be interesting to develop the closed-loop transfer function of the control system under consideration and plot its frequency response. This would allow the corresponding MP defined as the peak magnitude or resonant peak, and Fp defined as the peak frequency or resonant frequency at which MP occurs, to be determined. The closed-loop frequency response characteristics, including the resonant peak magnitude MP and the corresponding peak frequency Fp, are evaluated as part of the dynamic performance assessment of the excitation control system in accordance with the principles of IEEE 421.2. Furthermore, it would be also interesting to implement the same transfer function in Simulink and investigate system's response by applying a step signal at the summing point. This would provide an independent verification of the obtained gain Kp presented in this video. The calculation sheet in Excel used in this presentation is available for subscribers upon request. Please email me at the address below and I will be happy to send you a copy. dacia.tompsslab@gmail.com. Thank you for watching. If you like this video, please give it a thumb up. More videos are coming, so please subscribe to be notified of future releases.